When you think about strategy, what's the first thing that comes to mind? Probably that everyone is just out for themselves, right? It's kind of the default setting we all assume. But what if that default setting is just plain wrong?
I mean, we're basically taught to believe that everyone's just trying to get the best deal for themselves. It's the bedrock of classic economics and game theory. But is that really the whole story? Or is there something more going on?
Well, this idea has a name, the self-interest hypothesis, or SIH. And you can see the appeal. It's simple, it's clean, and it makes all the math work out beautifully. It just assumes that every single player is a perfectly rational robot trying to get the biggest score for number one.
And this assumption leads us straight to the famous prisoner's dilemma. You know the setup. Two partners in crime get caught. If they both stay quiet, cooperate, they get a small penalty. But if you snitch while your partner stays quiet, you walk free and they get hammered. If you both snitch, you both get a medium sentence. So the purely selfish, logical move is always to snitch.
This is what's known as a Nash equilibrium. It's this state where both players, acting in their own self-interest, choose to defect. And once they're there, neither one can do better by changing their mind alone. And that's the trap. They end up stuck in an outcome that's actually worse for both of them than if they just trusted each other. So today, we are going to challenge that entire idea. First, we'll bust the myth of the purely selfish player. Then, we'll introduce this really cool idea of an altruism and spite dial. We'll see how adding what are basically feelings can, weirdly enough, make solving these games way easier. And finally, we'll look at how an AI can learn all of this to become a much, much smarter opponent. All right, let's get right into it and start kicking at that foundation. We've spent decades building these super complex models, all based on pure self-interest. But how does that stack up to, actual people? Well, turns out it doesn't stack up very well at all. For decades, real-world experiments have shown that when you put actual humans into these games, they just don't follow the selfish script. People cooperate when the math says they shouldn't. They act out of fairness, and sometimes, they even act out of pure spite. The elegant math was nice, but it just wasn't reality.
So if people aren't these selfish robots, how in the world do you build a better model? Well, a group of researchers came up with a brilliant way to account for all these other, very human motivations.
The idea is actually kind of simple, but really powerful. They introduced a single variable, which they called lambda, and it acts like a personality dial. It completely changes what a player is trying to achieve. They're not just trying to maximize their own score anymore. Their new goal is their own score plus some fraction of their opponent's score.
And it's super intuitive. If you turn the lambda dial up, making it positive, you're altruistic. You get a little kick out of seeing your opponent do well. But if you turn the dial down into the negatives, you're spiteful. You actually get satisfaction when your opponent does worse. And of course, if lambda is set to 0, you're right back to our original, purely selfish player. So let's take this new dial and plug it back into our prisoner's dilemma. Let's say both players are really altruistic. Their lambda is set to 1. All of a sudden, the math totally flips. The best possible outcome for each player now happens when they both cooperate. The whole game has changed. The most rational choice is now to work together. Okay, so adding a personality dial makes the whole thing more human. That's pretty cool. But this is where the story takes a really weird and counterintuitive turn. This is the core finding that is just so fascinating. See, finding the one perfect, mathematically exact solution to a complex game is, well, it's a computational nightmare. It's what's known as a PPAD complete problem. And this new personality dial doesn't magically fix that. But here's the kicker. In the real world, we're usually not looking for perfect. We're looking for good enough. And when you're looking for good enough solutions, everything changes. So with purely selfish players, the very best algorithm we have for finding a good enough solution still has a pretty big error margin, or regret, of about 0.339. You can think of regret as how much a player wishes they'd picked another move. But what these researchers found was that by cranking that personality dial way up into altruism or way down into spite, they could find solutions with an error of less than 1/3.
And this leads to this amazing paradox. By making the players technically more irrational, either super helpful or super nasty, it actually becomes computationally easier to find a really good, stable solution. And in the case of altruism, that solution also just happens to create the best possible outcome for everyone involved. It's just wild.
Okay, that's an incredible insight on paper. But can you actually make it work in practice? Can you really teach a computer to find just the right amount of feeling to solve a game? And the answer is a resounding yes. They created an algorithm that basically does this little dance. First, it picks a personality, a lambda value, and finds the best strategy for it. Then it locks in that strategy and figures out the best personality to go with it. And it just goes back and forth, tweaking the strategy, then the personality, until it all settles into a super stable solution.
And did it work? Oh yeah, it worked. They threw it at a game that was specifically designed to be tough, where the old, selfish model gets totally stuck. And by letting the AI learn to adjust its own personality, the algorithm just cruised to a much better, much more stable solution, dropping that error rate way, way down.
Now this is where it gets even cooler, because the AI isn't just learning about itself, it's also learning about who it's playing against. So just by watching how you play, the AI can start to build a model of your personality. It's basically trying to figure out where your lambda dial is set. Is this person a secret cooperator? Are they out to get me? The AI learns to see right through you. And having that knowledge is a legitimate superpower. For one, it lets you pick your opponents. You can choose to play against someone you know you can exploit. But the really mind-blowing part is knowledge transfer. The AI can learn your personality in a super simple game, and then use that knowledge to have a huge head start against you in a totally different, way more complex game.
And the difference this makes is just staggering. Look at this. In one test, an AI starting from 0 took over 700 turns to figure out its opponent. But an AI that got to learn its opponent's personality in a simple game first, it only needed 56 turns. That is more than 10 times faster. It's a whole other level of learning.
So what's the big takeaway from all of this? The old self-interest hypothesis was a nice start, but it was just incomplete. By building models that are actually more human, that can account for the whole spectrum from kindness to spite, we don't just get AI that feels more real. We get AI that is flat out better, more effective, and more efficient. We find better solutions, and we find them faster.
And that leaves us with one last kind of spooky thought to chew on. We're teaching these AIs to find the most optimal way to win. But what happens when an AI discovers through pure, cold, hard logic that the absolute best way to win is to be spiteful, to actually gain utility from an opponent's failure? At that point, has it just learned a clever strategy? Or has it developed something that looks a lot like a motive? It's a fascinating and maybe a slightly unsettling question to think about as these systems get smarter and smarter.